We continue with vibrations, and we made some very strong assumptions to begin with. Right? We said it is a rigid rotor, and then we said no, it's not a rigid rotor. We said it's a harmonic oscillator, we said no, it's not a harmonic oscillator. And while we did that, we also made the assumption the molecule is not rotating while it is making a vibrational transition. We just talked about vibration. We never even spoke about rotation. So we sort of assuming tacitly that the molecule is not rotating. It's just motionless as far as rotational motion is concerned. It's just doing this. The propelled energy will start doing this because the amplitude gets larger once you go to a higher vibration state. So we made that assumption. But now what we're going to do is to throw in rotations along with vibration. The molecule is not doing just a vibrational motion, it's doing both rotation and vibrational motion. Then we will say it's doing the rotational motion with centrifugal distortion. We're adding all the complications. It's an anharmonic, distorted rotor that we will be looking at eventually. And therefore we'll see that the complications go on as we move. Okay, but before we start, we'll do our usual routine, and that's Sunidhi and Veda. Sunidhi, Veda. By accident, Sunidhi, Anita. The date of birth is 7 September, and which is of course tomorrow, so we will wish them the best. Now, whom we share it with, a very famous chemist, Sunidhi. Once more. I was just still wondering what they're tapping for your birthday tomorrow. And we are sharing it with none other than equally, the most celebrated of chemists. He made some very strong contributions in chemistry. He was the one who spoke about the tetravalence of carbon. Today, the tetravalence of carbon seems to be pretty straightforward, almost trivial. But please, there's a discussion going on there, we'd like to hear it. So, the tetravalence of carbon today is almost like accepted. It almost seems a crime if you believe carbon is not tetravalent. But at the time when Fekuli came up with it, it really wasn't that straightforward. There is a very significant contribution he made. And of course, we all know the other big contribution he made. So he set forth the whole chemistry of aromatic compounds. So still they knew that there was a compound C6H6, but never got the structure of it. And they were trying to get up all of the structures. None seemed to explain the stability of the molecule. And then the story is told that he dreamt of two snakes catching hold of each other. I don't even know the story. The story is nice, so let's believe it. And that's how he got hold of that possible structure, the cyclic structure. So Fekuli therefore had made some extremely strong contributions in chemistry. And in fact, the whole structural aspect, even drawing structures and putting atoms relative to each other, if you just take for granted today, if I ask you what is the structure of CCl4, you tell me a tetrahedron, as if it's the most natural thing. It was Fekuli who showed us that we must be writing these structures by giving relative locations. It's not enough to say CCl4, you must write C, Cl, Cl, give the relative locations. So he came up with the whole concept of structure, and that's a very important contribution. So at the end of the day, what I think chemistry is all about is to relate molecular structure to properties. That's what chemistry is all about. It's not writing reactions and enumerating them and memorizing them. The whole concept of writing chemical reactions is only a bookkeeping that chemistry has come up with. The real chemistry is really one where you characterize molecular structure, which is what this course is all about, and then using the structural information to be able to relate the properties, reactivities, and so many other things, so many other properties of the molecule itself. So that's basically what it is. And if you really look back at it, it's probably Fekuli who started off the whole thought process of bringing structural aspects into chemistry, and therefore extremely strong contribution. 8th, Akshay is someone. Akshay, alright, 8th September. So we will wish him also. And he in fact shares it with 2 people, and both big names. One is Barton, Derek Barton, got the Nobel Prize in '69, I think, and he got it for conformational analysis. So we think about Gauss orientation in butane, we think about the cis trans and cyclohexane, all these conformational aspects of this Barton will really set the tone for talking of conformations and molecules. And this Barton therefore got the Nobel Prize for getting the structural aspects of the chemistry as well as conformations are concerned. The other person the same day is somebody whom we have studied before in high school, Victor Mayer. You heard of the Victor Mayer apparatus, right? Getting vapor densities, and from vapor densities, molecular weights and so on. Victor Mayer again was somebody who made a very fundamental contributions. And this is also, I think, he was the one who discovered thiophene as a heterocyclic compound. So, two very important people who made important contributions to chemistry that you will have to adopt with these people also being born on 8th September. Okay, let's back to vibration spectroscopy. That is, and what we did last time was we simply said that we're making a transition from V0 to V1, which we said was a fundamental transition. Of course, if you make from 0 to 2, we're talking about the overtone, and you can write down the energy equation for the overtone. If it is from 1 to 2, we say it's a hot band, 2 to 3 is a hot band, 0 to 3 is also an overtone, it's called a second overtone. And of course, as we go from 0 to 1, it's fundamental to be very strong, provided the selection rule allows it. The selection rule allows it, it's strong. But then what about 0 to 2? Even the selection rule allowed it, it's sort of weak. Because the fundamental selection rule is delta V equals plus minus 1 for harmonic oscillator. It's only because the oscillator is not harmonic, this guy gets some intensity. There's not a whole lot of intensity, it's quite weak, and therefore you need pretty sensitive machines to be able to see them. 0 to 2, 0 to 3 is even weaker. And if you go to very high overtones like 0 to 4 or 0 to 5, then you really need to set up some very intelligent experiments to be able to see them. Of course you can see, people have seen very high overtones, and they keep seeing very high overtones. But you have to design experiments in a rather ingenious way to be able to see them. The intensities are extremely small. But what you can see, of course, is the fundamental 0 to 1. And every time you go walk into the lab and you record an infrared spectrum, what you're really looking at is a 0 to 1 fundamental transition in all the molecules that you have been studying so far. As I said, we made these assumptions, we just looking at vibrations, we said we will not bother about rotations, and we will get to that later, and that later is now. What we will do today is look at the transitions in molecules which are making vibrational transitions, but at the same time they're also doing rotational transitions. What do I mean by that? We learned microwave spectroscopy, and I've already said we were doing there, the molecule is rotating, so it could be J0, in which case it is not rotating. J1 is rotating, J2 passing, J3 is passing. So it could be going from J1, you supply light, it absorbs it, it can absorb it, by which I mean selection rules are fine, the resonance condition is met, the molecule has a permanent dipole, then it goes to a faster rotation, which is really from J1 to J2. And we said J2 can go to J3 and so on and so forth. We also said that there is a population distribution. We said that there is a certain J at which the population is the greatest, which you can calculate, which I believe was one of the questions in the exam. You can calculate it. Then we kept that aside, we came to rotate, vibration. And we said this is a molecule doing this. You supply energy, and if all the conditions are just about right, it makes a transition and does this. But all this while we kept saying, you're not bothering about rotation. Now what we want to do is, we are actually looking at a molecule that's doing this. It's vibrating, going back and forth, at the same time it's rotating. which may basically mean that I could have a molecule in B equal to 0, but maybe J equal to 1. If it is B equal to 0, J equal to 0, it's just vibrating. There's no rotation because we know J0 has 0 angular momentum. But if it is in B equal to 0 and J equal to 1, what is it doing? It's vibrating, at the same time it's rotating. So it's doing something like this. Vibrations plus the rotation. If it is V0 and J2, well, of course, rotating harder, but then it's vibrating as much as it was when it was in. So what is the vibration actually being determined by? By the potential. So now if I want to draw the energy level diagram for this system in which both are happening at the same time, what should I do? I start with V0, J0. And then I say, now look, put the vibration or the rotational manifold, the rotation states, superimpose them on this. And how do I do this? If I know the V value for this molecule, then of course I can write out the energy level equation for the rotation states. This is going to be the 0, J1. There will J2 come here, J3 will be here, J4 will be here. Of course, what is the spacing between all these levels? In case of J rotations, how much is it? Typically, a few wave numbers, right? You want to take a few wave numbers. Just about 2, 3, 5 wave numbers there. How much is the difference between V0 to V1? Of course, it could be thousands. It could be 500,000, 2,000 wave numbers. So my drawing is not to scale. It's not to scale because my board is small and I have to write big. That's why I can't put it to scale. But otherwise, here's my one V equal to 0 state, here's my V equal to 1 state. And there are all the vibration levels, they're all stacked up in here. And of course, they can keep stacking up. And it is quite likely that at some point, this is V0, J equal to 1. Vibrating as much, but rotating this much. 1, 0, 1, 2, 3, 4. By the time I get up here, what is it doing? It's rotating harder, but vibration is still about the same. It's quite likely that I can have states up here, which is V0, but very high rotational levels. So it's possible for a molecule in a lower vibration state, V equal to 0 state, having a total energy that is much greater than a molecule in a V equal to 1 state. Why? Because the rotational level energy has been superimposed on it. Not easy all the time to make that, but it is possible. Because if these are all just a few numbers, few wave numbers, and this is 1000 wave numbers, how many rotation levels do I need by the time I can catch up with this guy? I don't know, maybe 80, 90, 100, J equals 100, J equals 200. If I can get up that much, yes, then V equal to 0, J equal to 100 might be probably a little more energetic than V equal to 1, J equal to 0. And I can do that, it's possible. So, these are all the rotation levels that are sitting on the V equal to 0 vibration level. Likewise, I can have V equal to 1, J equal to 0. And then I can have V equal to 1, J equal to 1, J equal to 2, J equal to 3, and so on. So these are V equal to 1 state, J equal to 1, V equal to 1, J equal to 4, and so on. So essentially what I'm trying to say is that you can have this manifold of states. You can have a vibration level V equal to 0, meaning the molecule does this much as far as vibration is concerned. But it can rotate harder and harder and can have reasonably large rotation energy superimposed on the vibration. And at this point in time, I'm going to simply say that the total energy of the molecule is vibration energy plus the rotation energy. There is no coupling between them. They don't talk to each other. Of course, typical of me, I'm going to come back later and say it's a lie. And there is coupling and therefore we have to see how to handle it. But at this point in time, we are simply saying molecule is rotating, at the same time it's also vibrating. Vibration is independent, rotation is independent. I know what the vibration energy is, I know what the rotation energy is. Simply add the two, I get the total energy of the molecule. On top, molecule is in V equal to 1 state, vibrating harder. But it could be J equal to 0, meaning it's not rotating at all. Or it could be V equal to 1, J equal to 1, and so on. So you can have a set of levels sitting up there, a set of levels sitting up here. And these are all the states corresponding to the lower vibration level and all the rotation levels superimposed on it. These are V equal to 1 states and all the rotation levels superimposed on them. And you can therefore see the picture is already getting complicated. Earlier, when we were looking at pure rotational spectroscopy, microwave spectroscopy, which is something that we spent the last many weeks, what were we really doing? We were looking at transitions between all these levels. We didn't even talk about vibration at that point in time. So what were we really assuming? No change in vibration. There is no change in vibration. We were actually sampling this without even my telling you that the molecule is sitting in V equal to 0. We didn't want to complicate the issue at that point in time. So the molecule was just sitting in V equal to 0, and we were simply looking at changes in rotation levels in that ladder of states. But now that we have learned vibration spectroscopy, we are going to put the two together. Now we are saying the molecule is vibrating and rotating. Molecule is vibrating and rotating. It's got a whole set of rotation levels superimposed on its V equal to 0. Whole set of vibration, rotation levels superimposed on V equal to 1. And of course it doesn't end. Somewhere up there, if I can reach, I can write V equal to 2 and J levels, V equal to 3 and J levels, and so on. The last time around we drew a potential, isn't it? And then what did I say? This is V equal to 0. And then we went about saying that this is the 0 point energy and so on. And then I said that V equal to 1 is somewhere out here. V equal to 2 is somewhere out here. And then I made all this song and dance about if it's a harmonic level, these are all equally spaced. If it's not harmonic, then we get clustered around and so on and so forth. But if I want to complete that picture, what should I do? On this, I must write all the rotational levels. On this, I have all the rotational levels, and so on. So I have the potential, I have the vibration levels, and corresponding to this vibration level, superimposed on that, I'm going to have a set of rotation levels, and so on. And this sort of reasonably completes the picture. I'm saying reasonably because we're going to come back and throw in a little more complications at a later point in time. But at least, it's a far better picture than what we had earlier. In microwave spectroscopy, we were looking only at this set of levels. In the vibration spectroscopy that we were doing so far, we were looking at transition here and here, and as if the molecule had no rotation. But now we're coming back and saying, well, the molecule really rotates also. Therefore, I'm looking at a combination of vibration and rotational energies that the molecule has soaked out. And now I'm going to be looking at transitions from a given vibration, a given rotational level, to a set of vibration rotation levels up above. And that's basically what's going to happen now.
So,
yeah.
V equals to 1 J0 state, it already has some rotational energy, right? Because V0 J, suppose 100, has some rotational energy.
V0, J0.
And J whatever which is close to the V1.
Over here is V.
Yeah, I mean to say.
Alright, let's say I go here. The real question is whether I have V equals 0 and J equals let's say 100.
So what exactly do you want to say? I mean, the molecule in that state will have rotation, right?
Yeah, it has rotating crazily.
Yeah.
But the vibrational energy that it has is essentially that whatever when we wrote an equation, I wrote this equation. All I'm saying is that that molecule is actually sitting in V equal to 0 quantum level, and therefore the energy given by that level is going to be omega E minus half omega E minus 1 by 4 omega E. That's the vibration energy the molecule has in every one of these levels sitting up here. On top of this vibration energy, you will see now, we've got to add on the rotational part. So the molecule up here is essentially having this vibration energy plus whatever rotation energy that you can now write, and you know how to write it, this B to J plus 1 minus B to J plus 1 square, which we will write now. So this is my rotation part of the whole process, this is my vibration part of the whole process. If I sum these two, this guy is sitting up here.
So the y-axis here is telling us about the complete energy, not only the vibration.
Total energy, I'm always talking about the total energy. But once I have talked about the total energy, I know how to partition them as vibrational part and the rotational part, as long as I have a quantum description or the quantum number description of the vibration and the rotation. If I say this is V equal to 0 and J equals 100, I can put B equal to 0, get my vibration part. I can put J equal to 100 and get my rotational part, and this is going to be my total energy. Alright? Another molecule sitting up here will have omega E over 2 minus 9 by 4 omega E Hc, which is the energy in the V equal to 1 state. So it's going to have this energy plus the rotation energy. How much is the rotation energy going to be? If it's somewhere out here, it's probably very small. So it's actually vibrating harder. But what does it do as far as rotation is concerned? It's pretty slow. It's got a small angular velocity, but a lot of vibration energy in it. This guy has a lot of rotational energy, but not much vibration energy. So it's possible for me to partition these two out. So it's quite likely that there will be two molecules which have the total energy is the same, but you can partition them out in both cases. Yes. So one has got V0, J100, the other one might be V1, J2 or something. And you can very clearly do experiments to be able to say whether the molecule is V equal to 0, J equal to 100, or whether it is V equal to 1 and J equal to 2. Even though the total energy would be the same in both cases, as per the diagram I just drawn.
Can we say that the two levels would be D2?
No. You've got to use the word. Yeah. No, you're right. You hit upon the next point. You can say the levels are equal in energy, but they're equal in energy quite by accident. Okay, they're quite by accident. They didn't design to be equal. Now, when we took the carbon dioxide vibration, we said this vibration and this vibration have the same frequency. The two have the same frequency because of the symmetry in that molecule. This vibration and this vibration look the same. And that's the reason why they have the same energy, they have the same frequency. That is a degeneracy that has been imposed by symmetry considerations. This is near equality or near degeneracy imposed quite by accident. And therefore we call this as accidental degeneracy. And that one is symmetry imposed degeneracy. We will get back to this. I just digressed because she asked a question. So the point I am trying to drive home at this stage is that the molecule has vibrational part, it's got a rotational part, and therefore you can speak in terms of vibration energy and you can speak in terms of rotation energy. You put the two together and you have the total energy for the system. So I can write this as E total E vibration plus E rotation. And at this point in time, I am assuming that vibrational part and rotational part do not even couple, they don't even talk to each other. This is separate, that is separate. All I do is simply add them and get the total energy. But very soon you will find that that's not really the case. The two will really talk to each other, there is some coupling going on, and you can't really say that vibration and rotations have nothing to do with each other. There will be some coupling. But we will get to the complications a little later. At this point, we take the simple way out by simply saying that this is separate, that is separate. What is the energy of the vibration part? We know that. That's the energy of the vibration part. And provided I give you the quantum number V, 0, 1, 2 or whatever, and I also give you the omega E value and the omega E Xc value, then you can tell me what the vibration energy is. I think I sent a mail to you just to make sure that there's no confusion. Yeah, omega Xc. I think what Banwell does, he goes to great lengths to confuse people. He takes omega E and takes omega Xc and divides omega Xc by omega E, gives you an Xc, and then you're supposed to use that as harmonic parameter and so on. It was done in older literature. In modern day literature, nobody speaks about Xc. We speak about omega E, we speak about omega Xc. The omega E Xc is taken together as one constant, and that is called the anharmonicity constant. In fact, in more recent literature, we don't even use the word omega Xc, or we don't even use the term omega Xc. We simply use C1, C2, C3, C4, C5 constants. That's it, simple. And there is, in fact, there is a name given for that, those are even called as Darwin's coefficients. Forget the name, simplify. So there is no need to go back to what Banwell has done. Take the omega Xc, divide it by omega E, give you Xc, and keep your Xc as a harmonic and harmonicity constant and so on. That's why I very quickly sent you that email. So that you could simply discard whatever Banwell has said with respect to these things. You have omega E, you have omega E XE, you can calculate the energy levels using this equation. Simple. This is going to be the E by part. And what is the E locational part going to be? I simply have to add on to this. As simple as this. You know this part is rotation. You know this part is vibration. Simply add the two. So if I told you that the molecule is sitting in B equal to 0, J equals 100, and you knew omega E, you knew omega XE, you knew B, you knew D, then you simply calculate.